Hello! In this tutorial we'll be taking a look at the Bernoulli Gate, a VCV module that is based on the Branches Eurorack module by Mutable Instruments. I often use it in my patches to introduce some randomness. While there are a couple of tutorials that exist for this module, one of its features is usually either not mentioned or not given that much attention. And since I think this feature makes the Bernoulli Gate much more powerful and gives it significantly more flexibility, I'll be putting special emphasis on it. First I will give some explanation about the module and visually show the impact of some of the changes we make. And once the technical stuff is out of the way, I'll provide some samples of how we can use this by creating a patch from scratch with 3 voices that utilize the Bernoulli Gate. So let's start with adding the module and giving a quick rundown of the basics if you're not familiar with it. This module expects a gate signal on its input. I'll add a clocked module that will provide this for us. Set it to 60 beats per minute and use the first clock output as Bernoulli Gate input. Now every time that the Bernoulli Gate receives a gate on its input, it will send that at random to either the A or the B output. And how often the gate is sent to either of them is defined by this probability knob. When set to 50%, on average about half of the incoming gates will be sent to the A output, and the other half will be sent to the B output. If we turn this knob to the left, we tell the module that we want it to, on average, send more of the gates to the A output compared to the B output. And if we turn the knob to the right, the module will start favoring the B output more and more over the A output. And the module has an identical bottom section that does the same as the top section. Both of them operate completely independent, except for the bottom input. If nothing is connected to that, it will instead also use the input from the top section. If you do connect something to it, it will instead use that as its gate source. All other settings, inputs and outputs operate completely independent from each other. Now for the feature that gives the module that extra flexibility and power, the probability input. With a CV on this input, you can modify the probability that the module uses to determine which output to choose. The clearest way to show this is probably by visualizing it, so let's add in an oscilloscope by Count Modula. Connect the first channel to the B output and the second channel to the A output. Slow down the oscilloscope. Reduce the scale of the 2 channels so they fit better into view. I'll move the B output more towards the top and the A output more towards the bottom. You now get a clear view of how the incoming gates are divided over the outputs. Let's speed up the clock for now so we get some more gates. And you see that on average you get about half of the gates on each output. Let's add an 8-third module now to easily manipulate CV input values. Connect the first output to the probability input, and now if we start moving this knob to change the CV value, it will be as if we're moving this probability knob. Increasing it will make the gate start to favor the B output more, which you see on the oscilloscope, because the yellow gates coming from the A output show up less. And if you turn the knob to the negative side, it's as if you turn the probability knob to the left, and you have less red gates and more yellow ones. To explain exactly how this works, let's imagine that the probability knob goes from 0 volts at its minimum all the way to 10 volt at its maximum. So the current 50% would be 5 volts, and then you just add the incoming CV to that. So if we set this to 2.5 volts now, that means that this 2.5 volts is added to the 5 volts, which means that the total probability is at 7.5 volts or 75%. So more B than A. If we change the CV to minus 2.5 volts, you get the 5 volts on the module, minus the 2.5 volts of the incoming CV, so the probability is at 2.5 volts or 25%. And if you go to minus 5 volts CV, the end result is a probability of 0, so none of B and all of A. And you can still change the base probability on the module itself. If we set that to 75%, you get 7.5 volts on the module, minus 5 volts on the CV input, so the total probability is now 25%. And as you move the CV towards 0, you go back to the value that's set on the module. And when the CV is now 2.5 volts, that gets added to the 7.5 volts of the module, so all gates are sent to B and none to A. You can still move the CV further at this point, but that doesn't have any impact anymore, because this knob doesn't go all the way to 11. It won't go above 10 volts or 100%. Since all other functionality of the module has now been described, I'll also quickly explain what this button does. First, I'll reset the rate of the clock input to its default value. Now when you click this button, it changes the operating mode of the module. In the current default mode, every time a gate is received, it is sent to either the A or the B output, and that output stays on 10 volts as long as the input gate is high. If you click this button to change the mode, the module will always have either the A or the B output set to 10 volts. And each time that a gate is received on the input, there's a chance that it switches which output is high, and the probability defines how likely it is that the incoming gate will make the output switch. When you move that up, it is more likely to switch, and all the way at 100, it will switch on each incoming gate. And also in this mode, the CV input is combined in the same way with the probability knob. So setting this to -5 volts now will change the probability to 50%, and setting it to -10 volts will subtract this from the 10 volts currently on the probability knob, so it will never change. Now if we click this button again and reset everything, the module returns back to the standard mode, where each incoming gate is sent to either the A or the B output. And with that, we've covered all the details of how the Bernoulli Gate works, including that probability CV input that I haven't often seen mentioned elsewhere. So with all the technical stuff out of the way, let's actually start using this. Instead of using static input CV, we'll use a varying modulation source. Remove the 8-third module, and the first thing that comes to mind when thinking about modulation sources is an LFO. So let's add in an LLFO module by Bogaudio. Change its waveform here to a triangle. Let's hook that up to the oscilloscope to visualize it. And you can now see that the LFO moves up and down between plus and -5 volts. So that's perfect for using as the probability CV input. We'll slow it down by putting it into slow mode and change its frequency to 0.02 Hz, so it will take 50 seconds for the LFO to complete a full cycle. We'll increase the clock ratio to 4, so there are 4 gates coming every second. And now you can see that as the LFO in green goes down, there are more gates coming out of the A output in yellow. And as the LFO starts moving up again, more and more of the red gates from the B output show up, until it crosses over from negative into positive, and on average more red than yellow gates show up. So now we have to actually do something with these gates. And for the first voice, I'm going to use these outputs to trigger 2 different random melodies. One gate output triggering notes on one melody, the other output on the other. To start off, I'll add a sample and hold module by Bogaudio. This module expects a trigger on the gate input, and each time it receives a trigger, it will sample the current voltage on the signal input and hold that value on its output. And this module has a second part that provides the same functionality as the top part. If nothing is connected to the signal input, the module will instead sample a random value from an internal noise generator. You can specify the range of that noise generator in the right click menu. We'll set it here to 0 to 1 volt, so in notes that's 1 octave. Now we'll connect the top gate to the A output of the Bernoulli Gate and the bottom one to the B output. So now we can use this 0 to 1 volt output as note values for our melodies. But I want to make a distinction between the 2 melodies. Let's add in an oct module from VCV, set it to -1 octave, and use that to move the first sample and hold output 1 octave down. So now we have 2 random melodies being generated in different octaves. Since I'm going to play them using one module, I'll have to merge them into one cable. For this I'll use the MergeSplit4 from Grande. Connect the first melody line to it from the oct module and the second melody line from the bottom sample and hold. And now you can see these 2 melodies as voltages on the merge output. But these are random values, so they are not in tune. We'll have to quantize them to a scale first to make them sound a bit better. So let's add in a quantizer from VCV. Connect the merge output to it and set this to a C major pentatonic scale. So for that we'll need a C, a D, an E, a G, and an A. So all the other notes are turned off now, and we have the melodies ready to be played. Since there will be more voices added later on, I'm going to first add in a mixer now. We'll use the MixMasterJr for MindMeld, and since there will also be a send effect added, also add the AuxSpanderJr to it. Let's make some room for the effect, which will be a reverb provided by the Plateau module of Valley. Connect the input of the reverb to the AUX-A output and the output of the reverb back into the mixer. Turn off the dry incoming signal since it is a send effect and open up the wet reverb signal all the way. Add in a bit of modulation depth and close the highs and the lows on both the input and on the reverb. And the last thing to do is to hook up the mixer to the audio output. So now the mixer is ready to be used. For playback of the melodies, I'll use the Dark Energy module by Geodesics. The reason I tend to grab this module often for playback is of course because I like how it sounds, but also because it accepts a polyphonic input like we're using here. Let's reduce the level on the mixer a bit and hook it up. And then another big reason for using this module is that it has an internal VCA that you can enable here. So without any additional modules, you have polyphonic playback and a VCA that gets triggered anytime it detects a change on the input. And the duration of the VCA is controlled over here. A little bit less to 500 milliseconds. And now you can hear those two random melodies playing. The red B gates will trigger the lower octave one, and the yellow A gates will trigger the higher octave one. To make the distinction between these melodies even clearer, we can move them further apart. Split them when they come out of the Dark Energy module, and send one into the left channel, and the other into the right channel. And to make that split a little less extreme, we can change the stereo width of this channel in this right-click menu. Each melody is now a bit closer to the middle again, but still more clearly separated. Let's shape their sound a bit. Add some cross modulation on the left oscillator. Use the same 0.05 on the right oscillator, and also on the left self modulation. And for the right self modulation we'll use 0.25. Add in a good amount of reverb. And now we have two melodies that are being triggered by the Bernoulli Gate, with the LFO making those randomized triggers slowly favor one melody voice more, and then moving back to the other one again. And while the melodies themselves are nothing to write home about since they are simply randomly generated values, they do demonstrate the impact of triggering them with the modulated Bernoulli Gate. The way that I'm gonna use the probability CV input in the second voice is actually the reason why I originally started using it. And that is not to slowly change it over time, but instead completely stop gates from coming through, which is something I needed when triggering longer notes. To demonstrate this, I'll add in another sample and hold module. Set its range to plus and minus 1 volt, so that's 2 octaves. Trigger it with the bottom Bernoulli Gate, which in turn is triggered by the second clocked output. We'll also quantize these notes. Click and drag to disable them all, and only enable the C, E, and G. Connect the sample and hold output, and we'll play these notes using an FM-OP module. Connect the oct to the volt per octave input. Now the FM-OP has an internal envelope generator, but to generate the longer notes, I'll use the AD module from Bogaudio instead, which will generate an envelope to open and close a VCA by VCV. Connect the envelope output to the VCA CV input. Send the FM-OP through the VCA and into the mixer. Reduce the volume a bit by 9 dB. And now we'll have to trigger the AD module. We'll use the same gate as the sample and hold, Ctrl plus Shift drag to duplicate it, connect that to the trigger input. We'll mute the first voice for now. Make the notes longer by opening the attack to 2.5 seconds and the decay to 4 seconds. Switch it to linear, which I think sounds better here, and now we get longer notes playing. But I want single long notes to play. And you can hear that they change when a trigger is received, and the volume envelope also gets re-triggered. On the AD module we can fix this easily. Disable the re-trigger, and as long as there is an envelope still active, incoming triggers will not cause it to increase again until it is finished. But the same trick doesn't work on the sample and hold. Each trigger will change a note that's played. We need to stop the triggers at the source. So when a note is playing, no triggers come out of the Bernoulli Gate. Which is actually something we can control with the CV input. Let's add in a new module. The DGate from Bogaudio. This module accepts a trigger input and will generate a gate for it. You can specify a delay that it has to wait first, but since we want the gate to start immediately, that can stay on 0 seconds. And over here, you specify the length of the gate. So let's trigger it with the Bernoulli Gate output. And for the length, we want it to last 2.5 seconds plus 4 seconds. And let's add a bit extra and set it to 7 seconds. We'll show that gate output on the oscilloscope, scale it down a bit, and here it shows up in blue. So we'll use that 10 volt gate as CV input. But 10 volts means that the probability will be moved further to the right. So trigger the B output even more. But there's a simple fix for that. Move all the connections over to the A output. And now when the A output is triggered, it triggers the gate on the DGate module, which will move the probability all the way to 100%, which means that all the incoming gates go to the B output and none to the A output. So as long as there is a note playing over here, no new triggers come in. And when it's finished, there's a possibility again that the next input trigger goes to the A output. Let's change the base probability to 75%. So 3 out of 4 triggers go to B and 1 in 4 goes to A. Bring in the first voice again. To bring out the second voice a bit more, I'll move it up an octave by setting the frequency ratio to 2. Give it some punch with a bit of feedback. Also give it some reverb. And to give it a bit more of a fade out effect, I'll add in a chronoblob delay module. Connect the left and right outputs of the delay to the mixer. Switch the delay to ping pong mode. Send the VCA output into the right input of the delay. Use a delay of 1500 milliseconds. And let a bit more of the delay sound come out of the module by setting it to 0.66. Since the delay time is 1.5 seconds and the attack time is 2.5 seconds, that means that the left-right ping pong of the delay will fade in with that opening of the VCA, give it a little boost. And as the VCA closes, the delayed sound will start stretching out that decrease, giving it a bit more of a tail. I'm gonna change the probability for this voice to 90%, which means that more of the input triggers are sent to the B output, and so the A output will trigger for the second voice less frequently, resulting with, on average, a bit more time between the different notes. So now we have a Bernoulli Gate triggering a voice at random to play long notes, and the probability CV input makes sure that the voice doesn't get re-triggered as a note is playing. In the previous two voices, we used the Bernoulli Gate in its default mode, where it sends an input gate to either the A or B output. For this last voice, let's use the other mode where either the A or the B output are always active, and see one possible use for the probability CV input in this scenario. Let's first make some room. Also move this bottom row. and add in another Bernoulli gate. Click this button to switch it to the other mode and hook it up to the third clocked output. Now the outputs will switch between 0 and 10 volts at random times when a trigger is received. I'm going to use this to make a bass voice switch between a C and a G note. Playback will be done by the Instruo Ts-L module, which will have to provide a volt per octave input. When the B output is not active, it will be 0 volts, so that already matches the C that I wanted to play, but when the output is active, it will be 10 volts, which is a C 10 octaves higher, while I want a G, so we'll have to modify that. Which brings me to the Bogaudio Offset module. Connect that with the B output, so when the input is 0 volts, the output will also be 0 volts, but when the input is 10 volts, we'll have to scale that down. Now a G is 7 semitones above a C, and there are 12 semitones in a 1 volt octave. And the output of the Bernoulli gate is 10 volts, so we'll have to divide it by 10 times that. Thus, if we scale the input by this value, the 10 volts input will actually become the voltage of a G, and we can use that as input for the Ts-L. Reduce the volume on the mixer by 12 dB, and connect the wavefold output of the Ts-L to the mixer. Solo that voice for now. Open up the wavefolding bit to 0.2 to let it come out a bit more. So now you can hear the notes changing. But that's not a bass voice, we need to lower it. So let's set the offset module to -2 volts. That's better. Next, I don't want the notes to change that often. And it is changing that often because each clock input into the Bernoulli gate has the potential of changing between A and B. So let's reduce the number of times the clock is triggered. And if I want to reduce that, I need to set it to -4, not 4, so that a signal is sent for every 4 beats. But I don't just want to change the clock, I want to bring in some variation. Right after the note change happens, I want it to become unlikely that another change will happen. And over time, I want it to slowly become more likely that the note changes, which we can do with the CV input. When the B output is triggered, we need a signal that goes to a low value, and then as time passes, the value slowly starts to increase again. And when you combine that with the probability knob, it's as if you first move the probability to 0% and then slowly start opening that up again, until it changes the B output again and moves back to 0 and starts over again. That is a CV signal that we can actually generate with an LFO. If we switch that to a ramp up sawtooth wave and show that on the oscilloscope, you see that the signal goes to -5 volts, slowly goes to +5 volts, and then drops back to -5 volts, back up to 5 volts, and so on. Let's slow down the LFO. And now we need a way to make a change in the B output, move the LFO to that -5 volts position. I'll temporarily add a button module from little Utils to simulate that B output change. Hook up the trigger output to the reset input of the LFO. And now each time I click on the button, you'll see that the LFO output jumps back to that -5 volt position, because that's where it resets to. So sending a trigger on that reset input is exactly what we need to bring our probability down to 0. So all that is left is to let the change in the B output value cause a trigger signal to be sent to the reset input. And there's a module that can do that for us. Let's remove the button again. And we'll add in an Edge module from Bogaudio. Connect the input of the Edge module to the Bernoulli Gate output, and now the Edge module will monitor that input, and each time it detects that the value rises, so here from 0 to 10 volts, it will send a trigger on the rise output. And each time it detects that the value goes down again, so back down to 0 volts, it will send a trigger on the fall output. So combining these two triggers will be what we need for the reset input. Now, since VCV version 2.5, it is possible to send two outputs into one input, so we can just hook up those two trigger outputs with the reset input. But if you don't have version 2.5 and don't want to upgrade, you'll have to combine these two using a logic OR module and hook that up to the reset input. And now we can use this LFO output as probability CV input. But the signal is currently changing too fast to have the intended impact. Let's slow it down a bit so that its effect becomes clearer. Set it to 0.025 so that it takes 40 seconds to move from minimum to maximum. So now it will stay on each note for longer and slowly become more and more likely that the next clock trigger will actually cause a change to occur. And when that happens, the LFO goes back to its minimum value and again slowly increase the chance of a note change occurring, with still the randomization factor varying the duration of each note. Let's also do a bit of shaping on this voice. We'll use an LFO3 module from Grande. One thing I definitely want to modulate is the wave folding, so let's use the first LFO for that. Reduce the LFO rate significantly to 0.1 to make that more smooth. And I'm also going to add some FM modulation, making it wobble a bit. Use the second LFO for this, and we'll only need a little bit of FM for this, because if you start opening this up, you can hear that it quickly starts wobbling a lot. So we only need a very small amount. 0.005 will be enough. Slow down the frequency to 1 Hz. And then with the third LFO, we can do some modulation of the panning on the mixer. Make the movement a bit less extreme by moving the pan CV input level down to 50%. And also slow down that LFO to 0.1. Don't forget to add in some reverb. And finally bring in the other voices again. With that, we've now used the Bernoulli Gate in both of its operating modes, and used the probability CV input for 3 different purposes. These are of course only a couple of ways that you can use the Bernoulli Gate and its probability. As they say, the only limitation is our imagination. I hope you got some useful information out of this tutorial that you can use in your own patches. As always, thank you for watching and happy patching.